So, we are going to talk about also the integral for cotangent and write down the formula for that. Even though on the homework we did talk about the integral for tangent. We used u substitution by writing it as sine over cosine. And then we need to talk about how to do u substitution problems when there are bounds. Now there's an easy way, and there's a way that they might force you to do on the AP test. So I have to teach you two ways to do it. One way, if they don't force you to do the kind of harder way, it's not even that much harder, but it's a little bit different. And then the second way where they force you to, and I always, like I've seen a problem before where you have to do u substitution. But I always forget the way they formatted it and how they set it up, and where you have to actually change the bounds. And you'll see how we can change the bounds when we get to those. So on our problem, we could do it either way instead of being forced to do it the second way, because I can never remember how they set it up so that you're forced to do the second way. So we already came up with the integral of tangent. So since we did just practice on the homework how to find the integral of tangent, I want you guys to find the integral of cotangent so that we can come up with the formula for the integral of cotangent as well. I did make it negative just to throw in a little
spice.
Yeah. But when we write the formula down, we'll do the integral of positive cotangent, and it won't really be that much different.
So it's this one.
Yes. Okay. So when we integrate this, you should have gotten negative ln absolute value of sine x plus c. Now, if we're doing this as a formula, I threw in the negative just to add a little extra. But formula-wise, we would just say positive cotangent. How would that affect our answer?
It would be just
Positive ln sine x plus c. So if you would like to write that down as a note card as well, it's something, again, you could find without memorizing, or you could choose to memorize it. It does add speed if you choose to memorize it, but it adds to the quantity of things you need to memorize if you choose to memorize it. So,
oh, hey, I forgot the sign. It's sine of x. On the ln is the one that's sine of x.
This originally was sine. I don't know why. Yeah, this was supposed to be sine. I don't know why you changed this one. Okay, so then we approach the question of what do we do if we have bounds? What if we do not have an indefinite integral, but a definite integral? So, when we handle with bounds, there's two options. The first option is a little bit easier in my opinion, and that's to do the problem normally and then don't worry about the bounds until the very end. So option one, treat normally. Use bounds at the very end of the process. Okay, the second option is the option that they will try to force you to do at some point with a problem. And again, we learn so much, they only choose from here and there. This is another detail one where maybe they will, maybe they won't. Option two is to change the bounds. So they are in terms of u. If we're in terms of u completely, we never need to go back to x's. If we do the first way, we need to go back to x's and then plug in our bounds. So let's see the difference between the two. We're going to do the same problem 2 times and show the 2 different options. So option 1, we just treat it normally. So treating this problem normally, what do you think the inside would be? This one's tricky. This one's one of the oddball ones. Okay, so let's try that really quick. Don't write this down, but just to show what would happen. If we made u secant, derivative of secant is, so dx would be du over secant tangent. And if we replace back in, we get tangent times u squared times du over secant tangent. And what does not cancel? The secant. That's a problem. So this is one of the oddballs, because almost every time, if we pick the function that has the exponent around it, we're picking the right function. This is one of the ones where we try it, say, oh, not everything canceled, we're in trouble, we have u's and x's. So we would start over. So we tried secant, it didn't work. What's our only other option? Tangent. So now we're going to pick tangent. So then we get dx is du over secant squared x. So again, this one is an oddball problem. I chose it because it was an oddball problem. In almost 95% of the cases, the one Evelyn picked would be correct because it has the exponent. So just be careful and watch out for the cases where it doesn't work. Look for the times where you get u's and x's, and then you cannot integrate with u's and x's together. So we replace, we get tangent. Oh, we're replacing tangent. We decided tangent was u, so we get u times secant squared x times du over secant squared x. And now all of our x's do cancel. And I almost prefer, once we get u's involved with this method, I almost prefer not writing the bounds at all until the very end. Because I can't use those bounds with u's. They're not in terms of u. So just one thing to help me remember not to plug in the bounds too early. So then we integrate. What is the integral of u? 1/2 u squared. This time we don't need plus c because we are going to work with the bounds eventually. And what do we know about u? What does u equal? Tangent. So now I can worry about the bounds. After we integrate, when we have bounds, we evaluate using the fundamental theorem of calculus. So since we've already integrated, we don't need the integral symbol anymore. But we should have that evaluate symbol. That straight up and down line just means evaluate at pi over 3 minus evaluated at 0. So now we just do fundamental theorem of calculus. 1/2 tangent of pi over 3 squared minus 1/2 tangent of 0 squared.
Are those just, is that line mean bound? Or from?
This evaluate from 0 to pi over 3.
So you use that instead of the integral sign.
Because we've already integrated. We used it when we did fundamental theorem of calculus.
Right.
After you integrate, that symbol just means you're going to be plugging this in, pi over 3, into the function. You're going to be plugging 0 into the function. So now we have to remember our trig circle. What is sine at pi over 3? 6 is the, so I'm going to draw a mini unit circle. We really only need the first quadrant anyway. This is definitely pi over 4. Pi over 6 is down here. Pi over 4. Pi over 3. It's all over 2. And we start counting from top right or the top left?
Top left. I think it's top left.
I remember doing this. I remember having to learn how to remember.
That's the only part I always have trouble remembering. So how can we check with calculators right now? Someone want to grab their calculator, plug in cosine of pi over 3. We should get 1/2 if we set this up correctly. Or everyone's checking her unit circles.
You did it
We got it
right.
right?
Yeah.
Woo!
Last time you did it backwards, so I just thought you were
Okay.
doing the opposite.
So we start top left. You should remember, it's like writing in English. Writing in
Everything's
English,
over
we
two.
start top left. Okay, top left.
1, 2, 3.
So-
2, 1.
Tangent is sine divided by cosine. So square root of 3 over 2 divided by 1/2,
Square
which is
Times 2.
times 2. So we get square root of 3. So our first half we get 1/2 times square root of 3 squared minus, and then we also need tangent at 0. So our coordinate here is, this is the actual coordinate 1, 0. And this one we don't have to worry about. We just say, hey, this is, we know it's at 1. It's just whether x is 1 or y is 1. So we do sine over cosine again. 0 divided by 1 is 0. So minus 1/2 times 0 squared. After I move all of our trig stuff. That was just to help us figure out the values for tangent. We simplify. What do we get when we simplify? Three halves. So now let me show you the second option. Does everyone have this down before I scroll back up? So, option 2. We can change the bounds. Because we're doing u substitution, I can change the bounds and still be valid. So we still start out the same way. We still decide what u is, and we already went through the process of figuring out what u would be for this problem. Tangent x. We still find dx is du over secant squared x. But now we have to change the bounds. So if I'm going to change the bounds to be in terms of u, what function here could take something that's an x and make it into something that's a u? Something we already have written down would take something that's an x and change it to be a u. Tangent of x is equal to u. I know what tangent x is, and it makes a u. So if I take each bound and plug them in, usually I say like u of a and u of b, so I remember which one's the top bound, which one's the bottom bound. This is my notation and not standard math notation. So u of b would be tangent of pi over 3, which is, we found earlier, square root 3. So that will change our top bound. When we do all our replacing, this changes to square root 3.
And why doesn't that change 0?
We are going to change 0. I have not done it yet, no.
Sorry,
That's fine.
continue.
That is a good question. Obviously, we needed to do it. So, u of a, tangent of 0, which does happen to also be 0. That is not always the case. just in this particular problem. So yes, this bottom one stays 0, but not because we didn't change it to be in terms of u.
It's just because 0.
Just happened to also be 0. So then we do our replacing the same. We replace tangent with u. We replace dx, so we leave secant squared. We didn't replace that with anything. We replace dx with du over secant squared. I'm going to draw a line down the middle so it's separated a little bit more. So then we have integral from 0 to square root 3 of u du. And now I will do the fundamental theorem of calculus with my u's only. I do not have to think about x ever again in this problem. So I integrate like we did last time. The integrating is the same. Integral of u is 1/2 u squared. But instead of switching back to tangent x, I just integrate from 0, or evaluate from 0 to square root 3. I use the bounds that are in terms of u. If they're in terms of u, they can be plugged into problems that have a u. So now I just do fundamental theorem of calculus. 1/2 square root of 3 squared minus 1/2 0 squared. And we still get 3/2. So they're really not a whole lot different. But most of the time we like working with x because it's what we're comfortable with. It's what our brain's been programmed to do.
Since
So
second grade.
Yep.
Give or take a few years.
Okay, so I have one more try problem. And I am going to force you to do it the second way.
The second one.
The second way, in terms of u. Because we need to practice it. It, again, is one of those details you may see on the AP test, so we need to practice making sure we can do it. I don't know why it got all smushed together. So again, when we look at these, usually with a division problem, quite often the bottom will be u because they're trying to get a natural log involved somehow, the integral of 1 over u involved somehow. So most likely it's the denominator that's u on this one. Also, think about taking the derivative of the denominator. Derivative of 2x squared is 2x. I have an x involved. So most of the time it's going to be the denominator if it's a rational function. So I'm going to write the answer up and then help everyone individually if you have not finished yet. And then write the assignment up so that people can get started on the assignment if they want, while we still have some time left. So your final answer should have been -1/2 ln of 2. Yes, I did take the absolute value bars off on purpose because the absolute value of 2 is 2. And just for kicks, I could write it ln of 1 over square root 2, so ln of square root 2 over 2, just in case they decide some logarithmic rules would be a good way to reduce. Because really this is an exponent above the 2, which can change things. So assignment-wise, your assignment is page 343, 53 through 67 odd, and 71. So you may use either method you prefer on most of these. There is one that gives you the instructions to show both ways. So one problem you'll solve the same problem twice, both ways.
So 15 problems divided by 2, so 7, 8 problems? 8 or 9?
I said 9. Yeah, 9.